We'll wrap up our section on conics with a discussion about hyperbolas. So a hyperbola, though it doesn't look much like it, is really very similar to an ellipse. The difference in a hyperbola and an ellipse is simply that a hyperbola is the set of all points where the difference between their distances from two fixed points is constant. With an ellipse, the difference, it was that we were adding together to the distances from each point on the ellipse to the focal points. Here we're subtracting. Ultimately, that's the difference. A hyperbola can actually be thought of kind of like an ellipse that just wraps around infinity, if you will. It's not exactly how it's constructed, but like you can kind of see like this is sort of looks kind of like the part of an ellipse, and this would be the other part if it were wrapping around infinity. You can kind of think of it that way if you like, just to kind of see how these things are similar. Okay, we will look at the equation of We will look at the equation of a hyperbola very shortly here, but let me show you the things that are useful to know, and then we'll look at the construction of one in just a moment. So we have our center point, and the center is still located with the coordinates h and k, and those are still very readily identifiable from the standard form equation of a hyperbola. Then we have the distances a and b, and these are the distances along the, I would like to be able to call them the major and minor axis, but unfortunately these are labeled the transverse and the conjugate axis. So those are the distances to the vertices along those. Now, if you think about this concept of wrapping an ellipse around infinity, maybe it would help you understand here why we only have vertices along the major axis of an ellipse and not the minor axis. Possibly. It's up to you, however you want to think about that. But these are very similar concepts to one another. But anyhow, with the hyperbola, we have vertices a distance a away from the center, and then there's no point on the hyperbola this direction. In fact, what we generally do, and you can see this box already constructed, is we use this distance b to construct a rectangle. And of course it can be square, but most often it would be a rectangle, I think. And the corners of that rectangle set up the location of two different asymptotes that would pass through those corners. And I'm just trying to highlight them here. They're already drawn in. But those guide the actual hyperbola to infinity. That's what the point of those asymptotes are. So that helps us get a picture of what the hyperbola looks like. And in fact, what I generally do in drawing a hyperbola is come up with this rectangle first, and then the asymptotes, and then you need to determine if your hyperbola would be opening to the left and right, or up and down, which I'll show you how to do in just a moment. And then you can draw in the shape from those asymptotes. We do still have two focal points, and the distance between those focal points and the center is labeled c, but nicely, c squared is equal to a squared plus b squared in the case of a hyperbola, which is great because that is just the Pythagorean identity. But the thing is that it's really easy to mix up with the a squared minus b squared in the ellipse equation. So you just kind of have to remember one and the other. But apart from that, that's how we can come up with everything that's necessary for hyperbolas. I'll show you how to work with some formulas in just a moment. The next thing that I'd like to do is demonstrate for you the construction of a hyperbola. All right, so here's the basic construction. And one thing that I should have mentioned that I didn't, which is actually kind of important, the difference of the distances of each point on the hyperbola to the focal points, we take the absolute value of those. And the absolute value is important because that means that there's two solutions, which gives us both points on the hyperbola. All right, so I have set up here a conjugate axis and a transverse axis. I've decided that if I wanted to invert them, I would just have to like rotate the whole picture here, but everything kind of falls apart when I do that. So I'm just going to leave everything horizontal here. There's some sort of bug in this program, and I haven't gone through the time to get it corrected. So anyhow, to give you an idea how this works, what we can do is we can change the location of these focal points. We can change the location of A, but B is dependent upon what we choose for the focal points and A. All right, so I will just let's set it like that. That'll be fine. Now, what I want you to see as I move point P here, if you look at the distances between point P and each of the focal points, if you subtract those, you get the same number the entire time. So in this case, it's 2.76. And it's making that shape that looks kind of like a parabola, but it is, there's going to be two parts to it. Now to get the other part, we have to just kind of skip over here, but notice the distance between these points over here is still 2.76. Now this is a very steep hyperbola, but if you kind of imagine a line passing through B2 and B3, it would give us those asymptotes. And these points are approaching those asymptotes, and the other one here going from B1 to B4 as well. So that's how the hyperbola is constructed. If we wanted it to, be such that it is not quite as wide, we would just bring the point A closer to the focal point, and then it would not be quite as wide. But if you'll notice, this shape here, as we go out further, doesn't really resemble an ellipse, and it doesn't really resemble a parabola. So when I mentioned earlier that you can think of these things as like an ellipse wrapped around infinity, it's definitely not the shape of an ellipse, okay? It's just the concept is all I'm referring to there. Just so you can kind of take related ideas and see similarities, but they're definitely not the same shapes, okay? All right, now let's see how the hyperbola relates to a formula. So there's two different forms for this particular equation. We have basically the same concept in each one, but x minus h quantity squared over a squared minus y minus k quantity squared over b squared equals 1, or reversing the order of the y and the x. Now, one thing to note is that a squared is always under the first term. So a squared is under the first term. In an ellipse, sorry, it's hard to write and say at the same time. In an ellipse, a squared is the largest value, and whichever value that's under, that tells you if it's opening on the major axis or is horizontal, or the major axis is vertical. Here, it doesn't matter if a squared is bigger than b squared. There's no relationship there. A squared could be the larger of the two, or it could be the smaller of the two. But it tells me which direction my hyperbola is opening based off of which variable comes first. So if it's the horizontal variable first, x, we have a horizontal, and I did call this major and minor axis because, again, I really feel like it's much more concise when we call it that because it relates it to an ellipse much better. But again, I really should be like, this is the transverse axis, and then the conjugate axis. Either way, that's how we decide just which variable is showing up first in the equation. The only difference between the equation of the hyperbola and the ellipse is the negative between these terms. And that's ultimately the difference. Notice that, of course, like I said, c squared is equal to a squared plus b squared, which is really nice. And if you want to locate the foci, you can just use that equation to determine the distance to the focal points, and then add that distance to either the x or y coordinate of the center, depending on which direction you're opening. And that will locate the focal points. The equations of the asymptotes, there are formulas for these, and I have these listed for you, but I generally just simply draw the rectangle and then draw the asymptotes through that rectangle, and don't necessarily need a formula for that. Let's take a look at an example, and here I have an equation in general form, and I want to put it into standard form and then graph the resulting hyperbola. I will state the equations of the asymptotes at the end, but I'm going to do it differently than just defining by a formula. So here we go. First off, changing this from general to standard form is always the same. You use completing the square to do it. So separate out your x variables from your y. And move your constants to the other side. Factor out any leading term coefficients on the squared terms. So this would be x squared plus 4x. And then I would have negative 16 times y squared minus 2y equals 124. And then with completing the square, I take this number, divide it by 2, which is 4, and then add 4 here. But because it's being multiplied by 9, the net effect is adding 36 to that side of the equation. Similarly, negative 2 divided by 2 squared is 1, but I'm actually subtracting 16 from this side, so I need to do the same on the other side. So that means I have 9 times x plus 2 quantity squared minus 16 times y minus 1 quantity squared. And let's see, 36 minus 16 is 20, plus 124 would be 144. And then in standard form, we have this set equal to 1. So I would divide through each term by 144. So that gives me x plus 2 quantity squared, and that should be 16 minus y minus 1 quantity squared all over 9 equals 1. Okay, so the x variable comes first. So that means my transverse axis is going to be horizontal, because that's the horizontal variable. All right, the value of a is always the number below the first term, so a here is going to be the square root of 16, which is 4. B is going to be the square root of 9, which is 3. And then c squared is a squared plus b squared. So 16 and 9 is 25. Square root of 25 would be 5. So I'll just leave it as plus or minus 5 because, of course, there's 2 focal points. Now we probably have enough to put together a decent sketch here. So let's see what all we can do. So the center, the easiest thing, I didn't label what that was. The center is at -2, 1. Do some tick marks here. So -2, +1, there's my center point. And then the transverse axis is horizontal. So what that means is that the transverse axis, I'll just kind of shade that in like this. So that means my focal points are along the transverse axis. So 5 units away from the center on that would be 1, 2, 3, 4, 5. There's one focal point. And then 1, 2, 3, 4. Oops, a couple more points there. So 1, 2, 3, 4, 5. There's my other focal point. And I could very easily label those just by reading off the chart where it's at. So this would be looks like 3, 1, and this would be, I'll go ahead and label that. So 3, 1, and then going the other direction, starts at -2, -5, so that should be at -7. So -7, 1. Now, here's another thing that can be tricky, but there's an easy way of determining. So sometimes A is smaller than B, and sometimes A is larger than B. So you're not always guaranteed like which value is actually A and which one's B. But it's always true that the value A is under the first variable. And if that first variable is X, A is going in the X direction. So this value 4 would be 1, 2, 3, 4 units this way. 1, 2, 3, 4 units this way. And then B is in the Y direction because it's under the Y variable. So 1, 2, 3 this way, and 1, 2, 3 this way. This sets up an imaginary box. Well, I guess I shouldn't say imaginary. It's not like a complex number. It's not actually part of the graph. It's just helpful to use to get these asymptotes. And those asymptotes go right through the corners of this rectangle. All right, and I know that the hyperbola opens in the direction of the focal points. I've already got the focal points plotted, so here's my vertex. And I would just draw this graph going toward those asymptotes. Because the purpose of any asymptote is to guide your graph to infinity. Okay, now the last thing that was requested was the equation of these asymptotes. So honestly, at this point, what I do is just simply come up with the equation of lines. So, like for instance, I know that the center point is on both of these lines, which is at -2, 1. And then the slope of one of them, all right, so let's call this line 1. The slope of line 1 is, like for instance, if I was going from this point up to this point, well, actually even easier than that, if I went from the center up to this upper point, I would go up B and over A. So the slope is going to be a rise of B, which was 3, and a run of 4. This other this other asymptote, line 2, is going to have a slope where we would go up B and then back A. So it's going to be negative 3 over 4. And to get the equation of these, I can really just use this point slope form and say it's y equals, or actually, sorry, y minus 1 equals 3/4 of x plus 2, and y minus 1 equals negative 3/4 times x plus 2. And just solve them, in terms of y equals. So y equals 3/4 x plus 3/4 times 2. 2 and the 4 would cancel, so that's really 3/2. And then I would add 1 to both sides, but instead of adding 1, I will add 2/2. So I get y equals 3/4 x plus 5/2. And then the other side, I would have y equals negative 3/4 x, 2 over 4, that would be minus 3/2, but then I would still be adding 1, which would be the same as adding 2/2. So y equals negative 3/4 x minus 1/2. The same thing that you would have gotten if you would have used those formulas previously, but we have enough information to come up with the equation of any line as long as we have a slope and a point on the line. And we already have that information, so it's easier to just use stuff we know rather than coming up and memorizing yet more formulas. So there we go.